Welcome to the ePathshala lecture series in computer architecture. This module we are going to look at exception handling and floating point pipelines. So, the objectives are we will discuss generally about what exceptions are, we look at how Mips architecture handles these exceptions, we look at about other issues that might complicate the pipeline. So, what are exceptions? Exceptions are unwanted events which require change in flow of control, and different ISAs use the terms differently. Generally, exceptions arise within the CPU. For example, when you have an undefined opcode or an overflow occurs in an instruction, or when there is a problem with the system call. So, these are generally termed as exceptions. And when you look at interrupts, we normally refer to an interrupt that is raised from an external I/O device or a controller. And dealing with either exceptions or interrupts without sacrificing performance is very difficult and it has to be handled carefully. Now, we will not look at exceptions and interrupts separately. We will just generally use the term exceptions to refer to any type of exceptions or interrupts. So, to give you a feel of what these exceptions are, I will just give you some examples of these exceptions. An I/O device request is an example of an exception, and a problem in your OS service from a user program initiating or invoking a OS service from a user program is a type of exception. Your tracing instruction execution doing a debugging operation is an example of an exception. Putting a breakpoint in your program is an example of an exception. If you have an integer arithmetic overflow, that is an example of an exception. If you have a floating point arithmetic anomaly, that again is an example of an exception. The other types of exceptions are, it can be a page fault, it can be a misaligned memory access, it can be a memory protection violation, it can be using an undefined or an unimplemented instruction, it can be a hardware malfunction, or it can be a power failure. Now, all these are examples of exceptions, and as I told you earlier, we do not distinguish between the types of exceptions and interrupts, we just use the common term exceptions. Now, there are certain characteristics of these exceptions. We will first of all look at these characteristics. Exceptions can be synchronous exceptions or asynchronous exceptions. If an exception occurs in the same place with the same data and memory allocation, it is normally called a synchronous exception. Synchronous exception is a little more difficult to handle than asynchronous exception. Now, devices external to the CPU and memory generally cause asynchronous exception. An asynchronous exception can be handled after the current instruction and hence easier to handle. The other characteristic of an exception is whether it is a user requested exception or an automatic coerced exception. Now, some exceptions can be requested by the user. They are predictable and they can be handled after the current instruction. For example, breakpoint is an example of an exception, and we intentionally introduce breakpoints in our program, and this can be handled after the current instruction. Whereas coerced exceptions generally by the hardware, and they are not under the control of the user program, and it is harder to handle. So, the next characteristic of exceptions is whether the exception is user maskable or unmaskable. Some exceptions are maskable, some exceptions are exceptions that cannot be masked. So, it can be masked or unmasked by a user task. It controls whether the hardware responds to a particular exception or not. If an exception is masked, then the hardware is not going to respond to that exception. If an exception is not unmasked, then the hardware will respond to it. Now, the option of whether masking an exception or unmasking it is dependent on the architecture. You have certain instructions which will help you mask certain exceptions. The next one is whether the exceptions are within exceptions or between instructions. Now, some exceptions have to be handled within the context of a particular instruction. Now, it becomes very difficult to stop that instruction handle that exception and get back to that instruction from where we left off. So, handling an exception within an instruction becomes a little more complicated. Whereas, if you look at exceptions that will have to be handled between instructions, that instruction can be finished, you can handle the exception and get back to the subsequent instructions. So, they are much easier to handle. Another characteristic of an exception is whether it is a resumable exception or a terminating exception. A resumable exception is where we have to handle the exception and then get back to the program, you should be able to resume the program. Whereas a terminating exception is one which has caused some damage and it is a catastrophic exception and you cannot continue with the program, so you will have to terminate the program. Obviously, terminating the program is easier, so handling terminating exceptions is difficult, is not difficult, it is easy. Whereas resumable exception, because you will have to continue after the exception, it becomes more difficult to restart. So, having looked at the different characteristics of exceptions, we know that though exceptions in general cause difficulties, synchronous exceptions, exceptions that occur within instructions and resumable exceptions or restartable exceptions are much more difficult to handle than the other types of exceptions. Now, having looked at the various characteristics of exceptions, what will happen to exceptions in a pipeline? Now, as such, even when one instruction is being executed by the processor, when you have an exception generated by that instruction, you have to stop the program, you will have to execute the exception. Depending on what the exception handler does, you will have to, depending upon the nature of the exception, you will have to either terminate your program or resume the program. If you have to resume the program, you should have saved the state of the program and you should be able to resume. Now, when you are looking at a pipeline implementation, it is not just one instruction which is executing in the pipeline. So, you have an overlapped execution of multiple instructions. So, when there are multiple instructions available in the program and one of them raises a problem, raises an exception, it becomes much more difficult to handle. Now, exceptions are just another form of a control hazard. Now, suppose if you have an instruction like add register 1, register 2, register 1, and let us say that there is an arithmetic overflow occurring when this instruction gets executed. Now, you will have to make sure that register 1 does not get altered because there is an exception that has been raised. So, you should not be writing into register 1. But at the same time, because it is a pipelined implementation, you will have to make sure that the previous instructions that were let into the pipeline before the add instruction should complete without any problem. You should flush the add instruction and the subsequent instructions following the add instruction will also have to be flushed, and then you will have to handle the exception. So, it is similar to a mispredicted branch and we basically use the same type of hardware to handle exceptions. So, handling exceptions in a pipeline. So, normally when an exception has been recognized, an exception has occurred in an instruction in a pipeline, what we do is we force a trap instruction into the pipeline on the next instruction fetch. So, instead of fetching the next instruction, just force a trap instruction into the pipeline, and until the trap instruction takes off, make sure that all writes for the faulting instruction as well as the instructions that follow the faulting instruction are turned off. Now, this is done by placing zeros in the latches. Instead of writing appropriate control signals or other values, you just place zeros in the latches and prevent any state change till the exception is handled. This exception handling routine saves the program counter of the faulting instruction to return from the exception later. So, as soon as the trap takes charge, you have the exception handler coming into picture. The exception handler saves the PC of the faulting instruction so that it is able to return from the exception later. But if you are looking at a delayed branching concept getting implemented, it is not possible to recreate the state of the processor or subsequent instructions with just one program counter value because the order of instructions has been altered. So, in that case you will have to have multiple program counters needed with delayed branching. It is basically number of delayed slots plus 1, those many number of program counters will be needed. Now, look at an example here. So, for example, there is an exception handling on the data page fault, there is a page fault exception. So, as soon as the page fault exception occurs, the instruction that was let into the pipeline before that, which is the ith instruction, does not have any problem. It should be allowed to complete. But starting from the I+1th instruction, which raised a page fault, all other instructions will have to be squashed. All the other instructions that were already let into the pipeline following the instruction caused the page fault, all of them are squashed, and then you have the trap that is let into the pipeline at the next instruction fetch. Once the trap takes off, you will have the exception handler coming into place. Now, we also define one more term which is called a precise exception. Now, when an exception occurs, you know that the program counter of the instruction where the program has to be restored, that has to be saved, because you will have to get back to the program after handling the exception. And all instructions after that program counter value that might be in the pipeline must be converted to no ops, and other instructions should be able to continue. That is, the instructions that were let into the pipeline before the one that caused the problem should be allowed to continue. The instructions that were let into the pipeline after the one that caused the problem should not be allowed to continue, and they should be prevented from writing into doing any permanent writes into the registers or memory locations. Now, if you are able to recreate the state of the pipeline as an exception is generated, if you are able to recreate the state of the pipeline and start off wherever you left off, it is called a precise exception. Now, in this case, what should happen is the temporary program state not in memory, for example, registers, has to be stored in memory, and obviously you are going to have potential problems if a later instruction has already modified the memory or registers. How do you recreate the original state? That becomes a problem. So, a processor that fulfills all the above conditions is said to have precise exceptions. It is said to provide precise exceptions, and this is basically useful for debugging and of course for correctness. So, processors that support a precise model of exception behavior will allow you to start the pipeline at any point, handle the exception and restart the pipeline at the same point without any problems. But obviously, it is not always possible to do this. So, you might also have imprecise exception. So, precise exception, as we already defined, if you have the provision to save the status of the pipeline when an exception occurs, and if you are able to recreate the state of the pipeline after handling the exception, it becomes a precise exception. Now, if that is not possible, then we have an imprecise exception. Normally, processors have two modes of operation. They have a slower mode of operation and they have a faster mode of operation. Now, in the slower mode of operation is wherein we have support for precise exception. That is, the basic reason is because the processor may not allow certain overlapping of certain instructions. That is because it is not able to maintain a precise mode of exception. So, it will not allow you to do an overlapped execution of certain types of instructions. So, it becomes a slower mode of operation. Whereas in the faster mode of operation, it allows all instructions where it is able to recreate the state of the pipeline. So, that becomes a faster mode of operation or the performance mode of operation. In the slower mode of operation, because you have a restriction on the types of instructions that can be overlapped, it becomes a slower mode of operation. Normally, the precise mode or the slower mode of operation is about 10 times slower than the faster mode of operation. Now, having looked at the general issues related to exceptions and how exceptions cause problems in a pipeline, we look at what exceptions can occur in a standard Mips pipeline which we are already familiar with, and we will see how the Mips architecture handles these exceptions. Now, during the instruction fetch phase, you might have a page fault exception that is generated, you might have a misaligned memory access that is generated, or you might have a memory protection violation that is generated. In the decode stage, you may have an undefined opcode or an illegal or unimplemented opcode that is getting generated. This is an exception that will get generated at the decode stage. At the memory stage, execution stage, of course, you have an arithmetic exception, And at the memory stage, again because it is a memory access for data, it may again be a page fault on data, it might be a misaligned memory access, or it may be a memory protection violation. Write back normally does not generate any exception. Now, how are these exceptions handled in Mips? As far as the Mips architecture is concerned, the exceptions are normally managed by what is called a system control coprocessor, which has its own registers and its own instructions. Now, save the PC of the offending instruction or the interrupting instruction in a special register which is called the exception program counter EPC. So, whenever an instruction raises an exception, that PC's address, which is the offending instruction's address or interrupted instruction's address, is saved in what is called an exception program counter. And you also have what is called a cause register, which stores the cause of the exception. So, the cause register, depending upon the number of causes you have, you can encode all these values here. For example, we will just look at two causes. Let us assume that an exception might handle because of an undefined opcode, or it might arise because of an overflow. It is enough if we use 1 bit for this. So, let us assume that we are just using 1 bit of the cause register to distinguish between two different types of exceptions. As we increase the number of exceptions, obviously we are going to use more number of bits of the cause register. So, the Mips architecture basically uses two important registers. One is the exception program counter and the other one is the cause register. And whenever you have an exception that is raised, you have to, once an exception has been recognized by the processor, it will jump to the handler given at some particular address. Alternative to this, processors may also look at handling them using vectored interrupts. In the case of a vectored interrupt, the handler addresses are determined by the cause of the instruction, cause of the exception. So, for every exception, we are going to have a different exception handler's address. Say for example, if it is an undefined opcode, you might have an exception handler's address. If it is an overflow exception, then you might have a different exception handler, so on and so forth. So, every handler address is determined by the cause of the exception. Now, these types of exceptions are called vectored interrupts. Every processor handles it differently. Now, the instructions may either deal with the interrupt or you may jump to the real exception handler. Now, what happens when an exception is generated? Now, you will have to read the cause. Once an exception has been identified, you will have to read the cause of the exception, you will have to save the offending instruction's address, and you will have to transfer to the relevant handler, and then the relevant handler will determine what is the action that is required. The action will decide once you identified the action that is to be done for the particular exception, and then you have handled it. If it is a restartable exception, then you will have to take corrective action and use the exception program counter to return to the program. On the other hand, if it is a terminating exception, if it is a critical exception and it is a terminating exception, you are not able to handle the exception, you will have to terminate the program. You may have to do a report error using the EPC and the cause register values. Now, this is an example with the pipeline with exceptions. Now, because we have added extra features to the pipeline for handling exceptions, you can see that we have added extra registers here. The EPC register has been added, the cause register has been added, provision to flush all the pipeline registers have been added, because once you have an exception that has been recognized, you know that though the instruction causing exception and the other instructions following it should not be allowed to do any updates to the register file or memory. So, you will have to basically create a bubble there. So, zeros will have to be written into those latches. So, the flushing option has been included into all the buffers in the pipeline. And as you can see, the program counter also has an additional feature where it will be able to write control transfer to a predefined address depending upon the cause of the exception. So, you have that exception handler's address given as another option to the program counter. We already have multiple options given to the program counter depending on whether it is a normal instruction or a branch instruction. So, now we also have this feature added to the program counter's input to that multiplexer. Apart from this, all the associated control signals which will allow you to write into the EPC register, which will allow you to write into the cause register, all that goes without saying. You will have to look at all those control signals also. Now look at an example for exception. Let us assume that you have this sequence of instructions, and let us assume that the instruction at 4C, which is an add instruction, causes an exception, maybe an arithmetic overflow. Now what will happen when this exception is generated? Let us assume that if it is an overflow instruction or it is an illegal opcode, you have two different exception handler addresses given there. So the address at 180 and at 184, you have two different instructions given there, which will store different values into those memory locations. Now this is an example for your pipeline. So the add instruction causes an exception. So as soon as that exception is identified, the cause register is loaded with the cause of the exception. The EPC or the exception program counter is loaded with the address of the offending instruction, and then you have the flush options getting activated. So if you look at the next clock cycle, you find that the instruction that was let into the pipeline before the add instruction does not have any problem. That is progressing as such. Whereas the instructions that were let into the pipeline after the add instruction, you see that a bubble has been created. So no activity takes place there. So the program counter is modified with a new value depending upon the exception handler's address. So the control will be transferred to that point, and the exception handler will now take control. So the exception handler will decide what is to be done depending upon the nature of the exception. Now what are the other further complications with exceptions? So even with one exception, we have seen what are the complications associated with exceptions. Now adding to that, you also have other complications. It is not just that one exception will occur in a pipeline. You might have multiple exceptions that may occur simultaneously in the pipeline. An instruction in the instruction fetch stage may raise an exception. At the same time, an instruction in the memory stage may also raise an exception. So you may have exceptions getting raised simultaneously. And also exceptions may happen out of order. That is, an instruction that is let into the pipeline at a later stage may cause an exception earlier itself than an instruction that was let into the pipeline earlier. So how do you handle these cases? So, and because pipeline overlaps multiple instructions, it is quite possible that multiple exceptions will occur simultaneously, and out of order exceptions will also be there. Now the simplest approach to deal with such exceptions is we always try to handle exceptions in order. So the exceptions that were raised by the earliest instruction will be handled first, and then we will try to handle the exceptions raised by the later instructions. So try to handle them in order. Probably a status vector associated with each of these exceptions can be maintained, and you make a note of the fact that this instruction raised an exception. But until you have evaluated the other instructions in the pipeline earlier than this for exceptions, do not handle this exception. So that is how normally the out of order exceptions are handled. In complex pipelines, but this is not so easy to do, because in complex pipelines you have multiple instructions issued per cycle. We have been only looking at single issue so far, but you might have multiple instructions issued per cycle. You may have out of order completion, because when you look at floating point instructions and all that, the latencies are going to be different. So you are going to have out of order execution, out of order completion. So maintaining a precise exception model becomes more and more difficult. So whenever you have an exception, just stop the pipeline and save the state. You will have to save the cause of the exception and let the handler work out what to do, which instructions had exceptions, which are to complete or which are to be flushed, and this may require manual completion also. Now all this simplifies hardware, but the complexity goes into the exception handling software. So this is not feasible for complex multiple issue out of order pipelines. Now apart from exceptions, you may also have other complications arising in the pipeline. What happens if your ISA has complicated addressing modes? As an example, look at the auto increment addressing mode, which was supported by all the earlier ISAs. Now, in the case of an auto increment addressing mode, you know that as part of the execution of that instruction, after having used the contents of a register to fetch a data from memory or do some operation on it, automatically the register contents will be incremented so that it points to the next data in memory. Now, because of this update happening to the register file as part of the instruction execution, you have a problem in the pipeline, because all along we have assumed that writes to the register file happen only during the write back stage, and so we did not have other problems. But now if writes happen in the middle of an execution, and what happens if an exception is raised, then how do you get back the original value of the register state? That is not possible. So, the auto increment addressing mode complicates the pipeline implementation further. And similarly, because you are going to do in updating of the register file earlier itself, it may also add other hazards to the pipeline, a war and war hazard, which we did not have to handle so far. So, these problems also arise in the pipeline. So, any processor, latest processors which implement pipelining basically do not get into these complicated addressing modes. They do not have support for these complicated addressing modes. Similarly, if you are looking at memory to memory move instructions, many processors have support for memory to memory transfers, and it can be done as a string operation. You can have multiple bytes of data or words of data moved from one section of memory to another section of memory. Now, suppose if something happens in between, an exception is generated, it becomes very difficult to recreate the original state of the processor. You may not be able to restore the original values. So, all this becomes a problem, and if the processor does not have support to recreate the original state of the processor, then it will not allow you to maintain a precise mode of operation. And also long lived instructions where the latencies are very high will complicate the pipeline even more, because they may have partial states and you will have to save partial states, on interrupts, and that becomes complicated. Another complication that might occur in the pipeline is because of condition codes. Normally, we come across many processors where certain instructions, when they get executed, arithmetic and logical instructions, the result of these operations is indicated in condition codes. And based on these condition codes, you have a number of conditional branch instructions, jump instructions. Now, condition codes also complicate your pipeline, because when you are looking at condition codes, some other instruction, the order of instruction matters, because multiple instructions will modify your condition code. You will have to make sure which was the last instruction that modified the condition code, and you will also have to worry about how these instructions can be reordered. So, you have to be very careful while reordering these instructions. So, it becomes the reorganization becomes a major problem for the compiler. So, these are the other complications. So, last of all, one more complication and an important thing is a floating point pipeline. So, if you look at multi-cycle instructions, an integer pipeline had just one execution cycle. But if you are looking at floating point pipelines, they are more complicated instructions. So, they will have multiple cycles of execution. So, the fetch is the same, the decode is the same, then it will go through multiple stages of execution, and then it will do a write back. Probably if it is a load store, it will do a memory access also. Now, the additional complexities that arise because of these long latency instructions are, even if they start in order, you will find that these instructions will complete out of order because of the long latency or differing latencies of these instructions. So, if we assume that you have a division unit, multiplier unit, adder unit and a floating point integer unit, you will find that each of them have differing latencies. So, even if you are looking at an in order execution, you will find that they will complete out of order. Now, because of this, you have a lot of problems. One is because of the out of order completion, you might have multiple writes to the register file in a cycle. And because of more number of instructions available in the pipeline, they will lead to frequent raw hazards. And war hazards also come into picture because of the writes happening to different register files. War hazards, of course, are not possible because we always assume that reads happen in the initial part of the pipeline. So, we have war hazards, we have more raw hazards, and we might land up in imprecise exceptions because of the out of order instruction completion. So, this can also increase the width of the processor, because since there are multiple functional units, we also look at increasing the width of the processor, that is issuing multiple instructions every clock cycle. Now, all this adds to the complication. So, how do you deal with these effects? So, multiple writes to the register file, you can simply increase the number of ports, stall one of the writes during the ID stage itself, or stall one of the writes during the write back stage, and depending on where you stall it, the stall will propagate to the other stages. And war hazards, you will have to make sure that the hazards are detected during the ID stage and stall them for later instructions. Imprecise exceptions, of course, you will have to buffer the results, and if they complete early or save more pipeline state so that you can return to exactly the same place where you left off. To summarize, exceptions are unexpected events requiring change in flow of control. There are different types of exceptions available. We have looked at the different types of exceptions. We have discussed the different types of characteristics of these exceptions. All these exceptions will cause problems in the pipeline, and different architectures handle these exceptions differently. And adding to a complexity of a single exception, you may also have multiple exceptions and out of order exceptions arising in the pipeline, and you may also have instruction sets with complex addressing modes and condition codes which will complicate the pipeline. Last of all, we also have floating point pipelines which you cannot dispense with, but they add more complications to the pipeline, and all these complications will have to be appropriately handled. Thank you.